Today, we are diving deep into a secret language, the language of chemistry. You might not realize it, but it's happening all around us, constantly. And you know what? We're about to crack the code.
So let's kick things off with a little mystery. Think about these three things: a super bright, dazzling flame, a nail that's gotten all rusty, and yeah, even the air you just breathed out. They seem totally random, right? So what on earth could they possibly have in common?
Well, the answer is that they're all telling a secret story. And that story is told through something called chemical reactions. These are the things that are constantly changing, everything around us. And get this, by the time we're done here, you're not just going to understand this story, you'll actually be able to read its language. Okay, so where do we even begin with reading this story? Simple. We act like detectives. And what's the first thing a detective does? They look for clues, right? We've got to learn how to spot the evidence that a chemical reaction has actually taken place.
And lucky for us, there are some really obvious, telltale signs to look out for. I'm talking about things like a sudden change in color, or maybe something starts bubbling or fizzing. That's a gas being produced. Or, and this is a big one, a change in temperature. You touch the container and it's suddenly gotten hot, or even cold all by itself. Those are your smoking guns.
And what's really cool is that sometimes you get multiple clues at once. Take a look at this. You drop some zinc into acid. First, you see it fizzing like crazy. That's our gas. But at the exact same time, if you were to touch that flask, you'd feel it getting warm. That's our temperature change. So boom, two clear signs, one chemical reaction.
All right, so we've spotted a reaction. Awesome. But trying to describe it in a long sentence every time? That's just clunky. It's slow. So chemists needed a better way, a kind of universal shorthand, a secret language to talk about all this change.
Just look at this. The sentence on the left, it gets the job done, but wow, what a mouthful. Now look at the word equation on the right. So much better, right? You can see exactly what you started with, the reactants, and exactly what you ended up with, the product. It's simple, clean, and direct. But why stop there? We can make it even shorter, even more powerful. Instead of words, we use symbols. Mg for magnesium, O2 for oxygen. And just like that, you have a truly universal language. It doesn't matter if you're in Tokyo or Toronto, you see this equation and you know exactly what's going on. Now that is the power of a chemical equation. Okay, so every language has rules, right? Grammar. And chemistry's language has one big fundamental rule. It's a rule you absolutely cannot break, ever. It's the law that governs every single reaction in the entire universe.
And the idea is actually pretty simple. It says that you can't just make atoms appear out of thin air, and you can't make them disappear either. All you can do is rearrange them. So whatever you start with on the left side of that arrow, you have to end up with the exact same stuff on the right side. That's the law.
But that leads to a really common problem. You write out an equation for the first time and, the numbers don't match. It looks like you somehow lost an atom or maybe gained one from nowhere. So what do you do when that happens? Well, you solve the puzzle. You balance it. All right, let's put on our detective hats again and solve this puzzle. For our case file today, we're going to look at the reaction of iron with steam. Okay, here's our starting point. This is what we call a skeletal equation. And if you just count up the atoms, you see we have a major problem. We start with one little iron atom on the left, but we magically end up with 3 on the right? And we start with 1 oxygen and get 4? No way. That breaks our big unbreakable rule. We've got to fix this. So how do we fix it? We use something called coefficients. These are just the big numbers we can put in front of a molecule to change how many we have. Let's start with the messiest part, that Fe3O4. It has 4 oxygens. So to get 4 oxygens on the left side, we need to have 4 water molecules. Simple enough, right? Let's put a 4 in front of H2O. Okay, oxygen is balanced, but wait. Now we've got 4 times 2, so 8 hydrogens on the left. To fix that, we need 8 on the right, so we'll put a 4 in front of the H2. Perfect! We're almost done. Just look at the iron. We have 3 on the right, so we need 3 on the left. Let's just pop a 3 in front of Fe. And voila! Here it is, our final perfectly balanced equation. Let's do a quick check. 3 irons on both sides? Yep. 8 hydrogens? Check. 4 oxygens? Check. It all adds up. We've even added these little letters in parentheses to show if something's a solid or a gas, making our story even richer. Now this equation tells the whole true story. It follows the law
Okay, fantastic. So now you can read the language and you can even write it correctly. So what's next? Well, let's look at a few common genres. The different types of stories these chemical reactions can tell.
First up, we've got the combination reaction. This one is super straightforward. It's exactly what it sounds like. Two or more things combine to form one single new thing. It's like two characters in a story meeting and teaming up to become one superhero.
A really great example of this is when you add water to something called quicklime. They react, and I mean really react, combining to form one new product called slaked lime. And as they do it, they release a ton of energy as heat. You can literally feel the beaker get warm. That's a combination reaction in action.
All right, so if combination is all about things coming together, it only makes sense that our next genre is the exact opposite, things breaking apart. Let's talk about decomposition.
So, in a decomposition reaction, you start with one big, complex thing, and it breaks down into two or more smaller, simpler things. It's like our superhero characters splitting back into its original parts.
And trust me, this isn't just some boring textbook idea. It's huge in industry. Take a look at this. When you heat up limestone, that heat is enough to make it decompose. It breaks down into quicklime and carbon dioxide. And that quicklime, it's a key ingredient for making cement. Because we're using heat to do this, we call it thermal decomposition. Pretty important stuff, huh? So, after all this, you might be wondering, why should I care? Well, take a look at this equation. Does it look familiar? It should. This is the story of respiration. It is happening inside you, in every cell of your body, right this second. The glucose from the food you eat is combining with the oxygen you're breathing to make carbon dioxide, water, and, here's the most important part, the energy that's keeping you alive. You are literally a walking, talking chemical story. Think about it. The food you cook, the battery powering your phone, even the reason leaves change color in the fall. It's all chemical stories. And now you have the basic tools to start reading that secret language of change that's happening all around you all the time. So the only question left is, what other stories are you going to decode?